Hi, everyone. I am Dr. Bonita Sharif, and I'm going to talk about eye tracking in program comprehension. So I'm Associate Professor in the Software Engineering Research and Empirical Studies Lab here in the Department of Computer Science and Engineering. And let me start by first talking a little bit about how or what is program comprehension, how it differs from reading, let's say, natural text. So for example, here you have, you see a small snippet of code in Java, and it's basically showing you gaze of somebody reading this code. They're trying to comprehend it and trying to figure out what, if there's an error in this code. So this subfield, program comprehension of software engineering, basically tries to study how developers comprehend source code artifacts. There are some theories developed in the literature about top-down versus bottom-up program comprehension strategies, where top-down is usually done when somebody is familiar with the code and has already formed a hypothesis, whereas bottom-up is when they're not as familiar and building a hypothesis as they go. So we wanted to show the difference between code reading and natural text reading. So we wrote this paper in 2015 along with my colleagues. We tried to show if there truly is a difference, if we could operationalize certain metrics to show differences between natural language and code. So when we typically read natural language, we read it top to down, left to right in this manner. However, when we read code, it's not done the same way. It's much more nonlinear. So this was based on our hypothesis that people tend to read this in a different way. However, there was no systematic study to actually test and see if this was truly indeed the case. So this was the reason why we conducted this study in 2015. Teresa led this effort, the first author. And the two research questions we seek to answer in that study was if the linear trends that we observed in natural language held for novices that when they read source code. And then we wanted to know if the novices differed from the experts. So just an example of nonlinear reading here in a simple print pattern program. This has two for loops, as you can see, and it prints out a star. And it's basically has a main method and it's calling this function print method. So basically, if an expert read this, they would not read it top to down, left to right. They would go to the main method and then from there, jump to the function call and look at, what are the parameters and so on, right? So they would basically trace it in a way like the compiler does in execution order. So we wanted to determine, is it story order or execution order? So we came up with these set of variables that we tried to measure this linearity. Vertical next text, which is basically the percentage of forward saccades that stay on the same line or move one line down. Vertical later text is the percentage of forward saccades that stay on the same line or move any number of lines down. And the same thing with horizontal later text. This is basically the percentage of forward saccades within a line. We also looked at regression rate, which is the backward saccades of any length, and then the line regression rate, which is the percentage of backward saccades within a line. We also calculate two additional metrics, but I'm not going to go into that in detail. I have listed the citations, so you can actually read that paper. Just to get to the results real quick, because I want to talk a lot more about other things in program comprehension. We found a difference. We found that there is truly indeed a difference in these different measures between novices and experts in terms of linearity. So in the final findings in this study was when we compared natural text to source code, we found that reading source code was less linear than reading natural text. And even for novices, as they went through these learning modules that we had in this study, even the novices read it in a less linear form. We also found that people tended to read less elements in code. It was almost 60% compared to 80% in natural text. And then we also found that experts' reading behavior is better explained by the execution order rather than story order. Okay, so this is why I wanted to talk about this first, because I wanted to point out that there is truly a difference between how we read text and code, and this study actually operationalizes this through a bunch of metrics. So let's get back to software artifacts. So let's look at some software artifacts here on which eye tracking has been done before. Here you see a gaze plot of a UML class diagram and some source code. The circles denote fixations on these various points. We usually look at these with respect to an area of interest. So here you might look at how often did somebody read the prompt. Let's say that's the rectangle on the top left, or maybe these two classes together form some cohesive structure that people look at together, and so on. Similarly, for the source code that you see on the right, maybe you're interested in all fixations or durations in this particular switch statement. So when we talk about programs and how people read code, the areas of interest are typically these lines, or they could be parts of lines, as shown here. These are very different compared to images that are studied, in marketing, for instance. These areas of interest, as shown in yellow, are very different and are not the same even in terms of structure, right? So you can see the source code has a very unique structure. It's indented typically. And so we wanted to find a better way to actually support conducting studies in software engineering to support this program comprehension task. So let's start with the problem first. So the examples I showed you before, they're all small code snippets. And they have to fit on one screen. And if you've used eye tracking, you know that typically this is done with something that fits on one screen. Typically, there's no scrolling involved. And yes, if there's scrolling, they usually cache the page and so on. And there are other tricks done there. But for the most part, it needs to fit on the screen. This is a problem because oftentimes software developers do not work on just 10 lines of code. They work on many hundreds and thousands of lines of code and many files, and they switch between files and so on. So the current problem of using current state-of-the-art systems to conduct eye tracking studies for software engineering was that we could not switch between files. We had to do tons of post-processing later on to map the gaze to specific lines and sublines. Okay, as you can see in this small snippet on the right here, now you can imagine a file that is 1,000 lines long. That's going to take forever if you could possibly do that. So this is a problem. So the question was, how can we study realistic behavior in program comprehension? Because this is not how programmers work. And this is a threat to validity because, if we find some results on small code snippets, does this scale to larger code snippets? Or the larger ways how programmers actually work in the field? Okay. And if you see what software engineers do, they typically work in an IDE, an integrated development environment, such as this one. You can see here, this is Eclipse, and they have on the left the Project Explorer open with all the files. And then you can also see and read whatever file they open, they compile, and so on. Right. So basically, they fix bugs, they build new features, and maybe they enhance existing code. So they work with a lot of files and source code, not just things that fit on the screen. So this is why we came up with iTrace. iTrace is a community infrastructure that supports conducting large-scale eye tracking studies on realistic tasks within an IDE. So basically, we look at Visual Studio, Eclipse, and Atom. Right now, these three are supported. It supports the recording, the playback, and we have also now what we call the iTrace toolkit that does a lot of post-processing and filtering. Basically, it maps the gaze to the source code element. So for example, if you looked at an if statement, it will tell you that you looked at an if statement, or if you looked at a predicate and so on. So all of these things are very well defined. So the syntactic category of what you're looking at is given to you via this post-processing step. And we also have basic fixation filters that have been implemented. You can look at it at i-trace.org. So this is how it looks like. Basically, you are in your IDE and you can just do a quick calibration. And then this is just showing this for demo purposes. You can see the highlight. It's basically showing you, the reticle shows you where the person's looking at. The first study we actually used this in was in 2015. So in a nutshell, iTrace lets you connect to a tracker. It captures the data, all the raw data that the tracker gives you, and then you can process that data towards some functional code. Okay, and then do what you need to do and any stats and other stuff you need to do based on your research question. So this is great because now it lets you, it doesn't limit you to just 10 lines of code that appear on the screen. Now, in order to test this out, we actually conducted this study as a replication of a prior study that used shortcode snippets. This was published at ICSE 2019. I'm just going to briefly talk about what we did here and how it compared and how the results differ. So in 2014, Rodriguero and others did a study on code summarization. Basically, they gave people methods and that fit on a screen and asked them to summarize the methods. And the max length of methods was 22 lines of code. They used 10 experts. In our study in 2019, we used iTrace because now we could get longer, we could show longer methods right within the IDE. We used Eclipse for this study, and we basically found different results. I'll just talk about one result here and briefly cover the main findings. The paper covers a lot more. We had 4 research questions in there. But basically, as you can see here, when you don't show methods in isolation, people tend to look at call terms more. Versus if you showed them in isolation, people had no choice but to look at the method signature, right? So before, in isolation, method signature was the top thing people looked at, whereas when they were given the code in context with other code around it, they looked at call terms more. So this clearly changes the findings. Other findings, we also found that as the method body got longer, experts tended to revisit the body of the method more frequently than its signature. They also spend a lot of time reading call terms. They spent most of the time in the method they were asked to summarize, but then they also looked at class declarations, data members, and so on. So when given the whole context, this is why our paper talks about size and context matter, because given the context, people are going to look at those things. An even more interesting finding was that we could predict whether certain things in the code were used in a summary just by the gaze. Okay, so that's what I mean here is the gaze time on a line can predict if a line should be used in a method summary, which is really a great result because we see that developers look at things other than what they're summarizing, because code and related things to code or the method all build this mental model for this developer trying to understand the code. We have a replication package at that link if you're interested in looking at all the tasks and details of the study. So the bottom line here is replications are important, size and context matter very much, and maybe if we do single screen small code snippet studies, they might not realistically generalize to working environments. So this is a threat to external validity. So what is our vision for eye tracking in SE? How can we use this to determine context of how people are using eye tracking? For one, we want to add editing support because people don't just read code, they also write. But when you write, as soon as you press enter, right, you're changing your lines that are going to be under the gaze. So we need a way to be able to capture these snapshots. We have a recent tool demo paper at ICSE 2021 with our collaborators at Washington State that supports editing for Atom. You can check it out. We just put that out recently. We would also like to assess different types of software artifacts. And then how do we improve software tasks? So let me talk a little bit about how we can, what we can infer from eye tracking. We can predict task difficulty based on how often people look at certain things. We can, this is what I'm currently working on, we can predict expertise. For example, what's the eye tracking signature of an expert compared to a novice, for instance. We can use it to improve source code summarization as well as recommendations, which we have done. So the stars indicate areas that I've already been working on. But there are other things we can also look at, such as pupil diameter for detecting fatigue, or maybe just rereading regressions and those kinds of things. So there are tons of both raw features as well as derived features that we can use for software engineering tasks and build this context of how we can help the process. So what are the implications for practitioners? You can imagine an IDE that is more tailored towards your expertise level, for example, and then you could evaluate coding standards or practices on readability. For educators, you can use this to inform early curriculum and teach novices how to actually read code. Like we teach how algorithms work. And then eventually we build better theories to explain differences between experts and novices. We recently published this a practical guide on how to conduct eye tracking studies in software engineering. It's a great one-stop resource to read about best practices. And then this recent data set, it's one of the largest data sets that's available on code, but again, these are just short code snippets, but it's still a large data set, 200 plus data points here for analysis. Finally, I want to introduce my team. My PhD students, Nilfar Cole and Kangil. Visit our website to learn more about iTrace. Thank you for watching.